All right, hi everybody, we're back. All right. So the slope is the effect of a 1 unit move of the independent variable on the dependent variable. To find out the effect size, we just got to say how many units of the dependent variable or how many units of the independent variable we're changing. All right. So let's say Virginia goes from 70% college in 2015 to 75% college in 2025. We want to know what's the effect of that 5% jump in terms of what's it going to do to the number of female legislators we have. Well, we know that 0.938 is the effect of a 1 unit move of college on Wim Ledge. All right. We know here that 75 minus 5, we're moving 5 units. We're just doing multiplication. Then equals 93.8 or 0.938, excuse me, times 5 equals cheating. 0.938 times 5, 4.69. So this is good thing number one about regression analysis. We can use multiple regression analysis to specify effect size. Okay? Let's go back here. Okay? So the one thing is we can know, all right, if you change 1% of the percentage of people in college, what is that effect going to have on the dependent variable? The cool thing, though, comes when we start to analyze, when we start to use different variables. So let's go back up to analyze. We're going to go back to regression. We're going to go back to linear. Oh, hey, just like we said with SPSS, the variables are still in there. That the variables aren't in there. All right. Now, let's go down to black percentage. And let's move that. Oh, look, now we have 2 independent variables. How exciting. Let's go down and let's add Hispanic. Ooh, now we have 3 independent variables. Let's add one more and get really crazy, right? Ooh, percentage over 64. All right. So, female legislator. In here, we have college, black percentage, Hispanic, over 64. I'm going to hit OK. SPSS does wonderful things. Now, looking at these results, the first thing we want to look at, right? Let's just take percentage of population. Let me do it this way, okay? What multiple regression analysis does is that it simulates an experimental condition using math. In other words, it establishes through mathematics and statistics control groups and treatment groups. All right. What does that have to do with what we're dealing with right now? Let's look at our variables here. All right. Go back down to the third chart. First thing we always look at is statistical significance. So let's look at the college variable. Let's go across and let's say, oh, okay, look, the bullshit meter is at 0.000. That's lower than 0.2. Cool. We've got a real result. Now, let's look at our unstandardized coefficient. Always look at the unstandardized coefficient. Pretend the standardized coefficient does not exist. Unstandardized coefficient, all right? What this unstandardized coefficient is telling us is that for every 1 percentage point of the college variable that goes up, every time the college variable goes up 1, we get 0.831 more female legislators when we control for Black, Hispanic, and age over 65. In other words, this is telling us the independent effect of the college variable when we control for the percentage of a state's population that is Black, the percentage that is Hispanic, and the percentage that is age 65 or older. Okay? What's neat about regression analysis is that regression analysis tells us the effect of an independent variable on the dependent variable even when these other variables are controlled. In other words, this 0.831, somebody could come along and say like, oh, well, correlation doesn't equal causation. It could be because a state has a high African American population, or a high Hispanic population, or a high elderly population. With multiple regression analysis, we can say no. No, we are creating an experimental situation through statistics where we simulate 2 states that have the exact same percentage of Blacks in their population, the exact same percentage of Hispanics, and the exact same percentage of people who are age 65 or older. Then we are seeing the difference between one movement of the college variable when all these are controlled. In other words, because all of these are controlled, we're much more sure that one variable, that this is the independent causal effect on the dependent variable. What's neat about regression analysis is because you are starting to institute some controls, you are able to make some strong claims about causality. What's also neat about it is that SPSS calculates the independent effect of all of these variables even when everything is the independent effect of all the variables, all right? So let's look at this percentage Black, all right? First thing we got to do is look at the statistical significance. Okay, hey, look, it's statistically significant. Yay! Then we look at this unstandardized coefficient. What this is telling us is that when you create an experimental situation of 2 states, you control for college, Hispanic, and age 65 or older, right? An increase of 1 percentage in a state's population that is Black is associated with a 0.209 decrease in the number of Black legislators. All right? In other words, this gives you the independent effect of each of the independent variables on the dependent variables when all the rest of the independent variables are controlled. It's not quite strong causality. We can't say that we've gotten something causal for reasons we'll get into. But this is, say, how Billy Beane can start to be sure about which factors matters. He loads up everything that he thinks is going to matter in baseball, and then he uses those things to try to predict. He runs his equations, and he sees which ones of those have statistically significant effects on future baseball success when everything else is controlled for. All right? Now, this sounds great, right? This sounds like, oh, great. Why don't we do all of this? We can explain the whole world. Well, this leads to the primary problem with regression analysis, all right? And the primary problem that we have in regression analysis is usually something that we refer to as omitted variable bias. Omitted, as in O-M-M-I-T-T-E-D, I believe is how it is spelled, all right? What is omitted variable bias, all right? What we're trying to do right now is predict, scroll up so we can see it. Oh yeah, there's the dependent variable. We're trying to predict the percentage of state legislators who are women, all right? The only stuff that we are controlling for, the only stuff that we are testing are these 4 variables that are in the model. Well, look, we know that there's going to be more than 4 factors that determine the percent of a state's legislators who are women, right? We can start to name them. We can say, oh, maybe a certain state has particularly charismatic female politicians, and that would matter. That variable's not in our equation, so we're not testing for it. We're not controlling for it, okay? Our regression model is only as good as the variables that we have it in there. And if we are missing variables from a model, we are not going to be able to account for it. Therefore, our statistics are going to be limited. All right? Luckily, regression analysis has a way that we can start to know how much omitted variable bias is messing with us. And that is with the statistic up here, called the R-squared. Right? The R-squared is a number that ranges from 0 to 1. Right? It is, again, permissible to think about the R-squared in terms of percentages. The R-squared tells us how much these 4 variables right here, if we know these 4 variables, if we know in a state the percentage of people with college degrees, the percentage of people who are black, the percentage of people who are Hispanic, and the percentage of people who are 65 or older, if we know those 4 factors, the R-squared tells us, if we know those 4 factors, we can predict this percent of the dependent variable. What this R-squared is telling us, if we know these 4 things, we can predict 46% of what we need to know in order to... This explains, let me start again. These 4 factors explain 46% of the outcome of the dependent variable. If we know these 4 variables, we know 46% of all there is to know in what makes up the percentage of state legislators who are female. Now, is 46% a lot? Your first blush may be, well, no, not really. Like 46%, these 4 factors give us 46%. Like, you know, that's not even 50%. That's not really all that good. I would submit to you, though, that just knowing these 4 factors, right? We know, just knowing 4 things, 4 basic numbers, we have explained 46% of the entire universe of factors that determine what percentage of the state's legislators are women. All right? That's pretty good for just 4 factors. And you can imagine that if we put more factors in here, we would start to explain more of the outcome, right? We would start, if we had 10 factors, maybe we get this R-squared up to 0.65, all right? Or something like that. In other words, this tells us 46% of the story just from knowing these 4 factors. And for the other 53% of the story, we can use other methodologies, right? Maybe we go to Feno and we start interviewing people. Maybe we, do a survey or something like that, all right? I don't want to give you sort of thresholds for what's a good R-squared and what isn't an R-squared, just as long as you understand that the R-squared tells us how much the independent variables, what percentage of the outcome of the dependent. I'll start again. What percentage of the dependent variable do the 4 independent variables, or all of the independent variables, if you have more than 4, explain? That's the R-squared. I think that's all I got for you today. If this is not confusing, or if this is confusing, look over your notes, watch this again, read over your book, and I promise that it will all look more easy, it will all look nicer once you see me work through the stats lab. Okay? Have a great night, and I'll talk to you soon.